Welcome. I can't believe it's July already. And I'm at a conference with Vince and talking about Aurorasaurus. Excited to talk about Aurorasaurus with you guys. I left my poster downstairs and came up here to make this call. So that's exciting. And then we've had a lot of interest in the data and all of these, how it compares to people's models and different events that people are studying. And there's a lot of interest in the large events too. So I'm going to launch into just a explanation through the figures in our new paper. And our new paper has this data release, and it has a look at the two different largest storms of the last solar cycle. And so it takes you through our whole data processing process and kind of looks at the statistics, and then all of this data is available for download. And then we also made available some code through something called the Jupyter Notebook that runs Python code and you can reproduce these plots if you want to. Or make other plots. So there's definitely some interest in that. Some people are so interested in the data, they just want to get their hands on it themselves and not read the paper. But we're going to go through a little bit about what the paper looks at. And okay, so we have a huge number of reports, over 6,000 reports from the Gannon storm in May of 2024. And then we have 1,700 reports from the next biggest storm in October. I'll talk about why that is in a sec. But we also see just the pie chart here shows that over 50% of people who reported saw the aurora and uploaded an image for the storm. So that's really great. And 17% of people saw the aurora but didn't upload an image, which is also fine because you all know that we have the precise time and location. And 30% of people weren't successful at that time, but they reported. So those data are also valuable. I'm going to skip the next one, kind of go through these quickly. So then we have a data cleaning process, and my post-bac student, Firas, who is now in grad school, but he processed all this data and flagged some of the data because a lot of things happen. Sometimes there's erroneous reports, or maybe there's spam, or maybe there's personally identifying information, and we want to scrub that out of the data set. So in this chart, it shows some of the categories of data that we scrubbed, some of which, there could be duplicates in the data. And so we had a process of looking through all the reports and seeing if there might be duplicates. Potentially that was up to 7% of the data, but in actuality, it was more like 1% of the data was actually duplicates. So that wasn't a big deal. Some of the reports have a really long time associated with them, and that is harder to use to compare to the geophysical data because you don't know very precisely when that occurred. So we actually filter out data that was more than 12 hours in time. And then some of the no reports, people reported that it was cloudy or it was bright from light pollution. And that data doesn't help us determine if aurora was visible or not, as much as a no, I didn't see it and the sky was clear. So we remove all of those reports as well. And then when you see the percentage that was removed, for those three categories that I talked about before. The blue is what was original, and the purple here is what is the clean data. So we remove a little bit of the data. There's different proportions. The largest section that gets removed is in the no category. And again, that's just because these were the ones where they said no, but it was cloudy. And that is, I will emphasize, that's actually useful in real time because it's useful to others who might be curious where the reports are coming from, but which is why we keep it and why we want you to report it, but we don't want that for the most cleaned analysis data set. And then we looked at the reports as a function of time during the storms. And so for the Gannon storm, we see the most reports, and these are on the x-axis here. The time is in UTC, so they're all in universal time, and then the number of reports is on the y-axis, and the yes, I saw Aurora is the blue reports of the clean data, and the no's are the red reports, and you see some fluctuations here, and fluctuations with time over several days that this storm happened. And I can ask if anybody has some guesses as to what that reflects. What those fluctuations reflect. Time zones.
Where it was nighttime.
Yes, I knew y'all knew that. But yeah, as the Earth turns, there's not much landmass over the Pacific Ocean, and it's when it's nighttime for us and when we have reports. So yeah, you can see that because we do have the most reports in the Northern Hemisphere and the most reports over Europe and North America. And then the other thing on this chart is what's called the DST index, which is a storm time index. Actually, I lied. It's actually one called the SIMH index, which is the faster version of DST. So it's a 1 minute index, whereas a DST is slower. But this shows how big this storm is. And this storm was really, and when that storm peaked, storms have different characteristic shapes in this index. So it's generally pretty quiet. And for this black line, you look at the right-hand side, so it starts around 0. And then there's this characteristic upswing in the current that's sensed in these magnetometers around the equator. But then it drops, and this is actually due to the ring current response to the storm, and it drops rapidly here to its minimum. This is called this indicates the strength of the storm overall, if you ever hear DST minimum. And this first phase of the storm is called the main phase, and then the storm recovers, so that's called the recovery phase. A little different than substorms. Then we also plotted, we had some website outages during these storms. So this gray line shows when that happened. We probably missed a bunch of reports during those outages. And then the time when we had the most reports, when the website came back, is the time of the DST minimum of the kind of like peak crazy aurora there. And then the next storm is shown on the next chart, which is similar, although the overall numbers of reports is quite a bit less, and the outages, unfortunately, we had like major outages during this storm. So the number of reports is a lot less. As a result, we have a lot fewer no reports, which is fine because, after the fact, you're not going to want to report no's as much. But yeah, we could still use more reports from this storm, but we still have 1,000 is still a lot. Okay, so now we have, there's some suggestions. It would be cool to see the chart only for the middle latitudes. That is absolutely a good subset of the data that someone could run. And part of the reason that we put this data out openly is because, like, Bhagyashri, you can make that plot like right now. No, but anybody can, if you have some coding, can kind of work on how they want to present it, or take suggestions and work together on that. Okay, so then those questions that we ask you all about what the colors were, what the auroral activity was, the form that we have, where in the sky the aurora was, and the different types of aurora, that is plotted in the next chart here and compared for the two events where there's pairs of data for each of those questions. So I won't go through it all, but we see that some of these questions you can select all, right? So on the auroral color, multicolor means more than one color was selected. And you can see that's the vast majority of the reports for these two storms. And then you can also see, you know, people skip these questions up to a third of the time. So that's the yellow on all of these answers. And then, of course, these descriptors are not, you know, perfect, but they're guidelines to what happened, and there are further ways that you can, that are useful, that you can then like dissect or cut into the data set the way you might want. So for instance, there might be a researcher here who's interested in comparing these points to during the different storms to where the aurora was. And so maybe you only want to look at some of those overhead or whole sky reports on this third set of answers here. And then you can compare that to an auroral oval model or other corona pictures, other things. I will also say the photos are not in the publicly downloadable data set, but we are making those available on request to researchers, and we just ask that people don't put all that on the web per the usual terms of use that these data were collected with. Okay, so I'm gonna move on unless somebody wants me to talk to any more of these charts. This chart, which I can. We see different distributions for different types of storms. These are very large storms, so you know, it looks different than like if you look at all of the data, which you can also run this type of chart for any type of time period that you want in that code that we have. Okay, so now we get to some of the just points on a map of yes, I saw aurora versus no, I didn't. It's hard to make those plots. You could also think about making binning these in different bins. We've looked at that a little bit as well. But we see a bunch of reports here. You can start to see where some of the extreme low latitude positives and negatives were. And there are also a lot of people who are interested in where these lowest latitude observations were, what those in particular look like, when in particular during the storm they were. And I think one of the points I tried to make in the paper is that this data set, because it has time so well and location so well, that you can get a better sense of where and when the most extreme aurora during the storm was. And you can also see, I think, from the fact that it's distributed around the globe, that for many hours during the peak of this storm, the aurora was at very extremely low latitudes. And then, similar distribution, but a lot fewer points for October 10th. That storm also started maybe a little bit earlier in the night, so we got a lot of reports from Europe. It also wasn't as large, so there aren't as many low latitude reports. We have a great response from the UK as well, and there's even more points that you could zoom into there about where people are seeing it, where they aren't, maybe things to look at with light pollution, things like that. Okay, so then we also examined the number of observations, and then we just looked at one parameter, which is not the normal latitude that we're used to, but what we call geomagnetic latitude. And that is relative to the Earth's magnetic pole. So again, seeing the distribution of points down to very low magnetic latitudes during this storm, there's like a sprinkling of observations below 30 degrees here. Of course, more no's than yeses, but some yeses as well, some singular yeses. And then you can see like the most reports have some peaks at particular latitudes, and that tends to be where like if the aurora showed up over London, everybody's reporting, a huge number of people are reporting at those particular latitudes. And that's why it's a little bit choppy there. These data are always meant to represent not the absolute distribution of where aurora is in the world, but they have basically like population bias built in to them, or an unequal distribution of population, because people are distributed differently, and where there are more people, you get more reports. So that could possibly be something to like normalize in this chart as well, like how many people there were at these different bins, or how many people would potentially have reported, but it gets complicated with that too. And then we also looked at the distribution for the May storm of what time people report. And here we convert the time, again, in this magnetic coordinate system. We convert it to magnetic local time, where midnight is everybody's peak time for seeing aurora, or generally looking at the peak time for seeing aurora. But most people, if you look at the actual chart, most people are seeing aurora at, I don't know, maybe 19 to midnight, and then kind of peaking around 2100 hours, so 9 p.m. And I think this also would change if you look overall, or if you look at different storms. So yeah. And then kind of a couple more charts here, just a couple more. We also looked at the range of colors seen in different locations. And then we did kind of a comparison between these two storms, because we ourselves saw differences in what colors were seen, and we were curious about that. So, you know, you all recall the May storm and you recall the October storm, and kind of one of the points that we're trying to make here is the sky is a lot lighter during the May storm, and there was also like more blue because there's more sunlight at high altitudes potentially, and then that causes more, can cause more blending of colors. So we think we see a little bit more purple and pink relatively during this event than during the October event, which I'm about to show you. So this is the October event. There is less purple, a little bit less pink, less blue, largely, but go back and forth. They look different. And again, this is something that people can delve into a lot more. And then there are a few differences in blue and purple. I'm not sure that those were, like, I think we scraped the data for if people wrote in those colors. So those might be undersampled here because that wasn't on the form itself. But there's interest in both of those colors, as you all know. And there's some other work, some other research that people have done, like in Japan, they've looked at the amount of blue aurora they saw and the amount of magenta aurora that they saw as well. Let's see what else we have. Yeah, that's pretty much it. I'm trying to think. The other point, I'm trying to think of the other points that are on my poster. The one other point that's on my poster is about how this data set can, even in the month or so since we've made this public, people have looked at the data, people have found things, people have expressed interest in looking at the data in different ways, and that is part of the whole idea of it here.